Homework 2.3, linear functions and slopes, video number 1. Homework due Friday, May 22nd, 2020 at 11:59 p.m. So we're about to talk about a specific type of function called a linear function. And at some point between now and the end of this video, I should make a note in my table of contents off the screen here, we'll actually define what a linear function is, but we're going to start out by discussing slope. Now this is a concept that many of you may already be familiar with, and I'm confident that all of you have seen it at some point between the time you were born and now, because it's standard material for a high school Algebra 1 class. A couple of things about slope before we actually get into some calculations. If you ask people who know about math what is slope, you'll get a variety of answers, but the best answer in my opinion is what it's attempting to measure. Slope is the measurement of the steepness of a line. So anytime you calculate a line's slope, you're coming up with a number to describe how steep it is. Now from a geometry perspective, you could measure the angle it makes with the ground, but in order to get to the angular perspective of slope, we would have to get into some trigonometry. So we won't be doing that. Also, and some of you already know this, in algebra, slope is usually represented by the letter M. There's some theories as to why the letter M is used. A common theory is in French, the word for mountain, the word for climb is monter, which starts with M, as in climbing a slope. And in a minute we'll get the formula for the slope, but you may already know what it is. But let's take a look at a specific example. On the board I have a line that contains the points 2, 4, and 9, 8. And if we're attempting to measure how steep the line is, there's a few ways to go about it, one of which I mentioned is to measure an angle, but we're not doing trigonometry. Another way is to compare two measurements between these 2 points. One of them is how far you would travel horizontally from the first point to get to the second point, and the other measurement is how far you would travel vertically to complete your journey from the first point to the second point. The distance you travel horizontally is commonly called the run. It's like you're running in that direction. And the distance you travel vertically is commonly called the rise, which gives the suggestion that it's always elevating, but sometimes it might go down if the rise were negative. So it stands to reason that one way we could measure the slope of a line is to compare these two values. If we were to compare the rise and the run and we had a steeper line, then the rise would be bigger. So whatever we set up, a larger rise means we need to have a larger slope. The way to compare rise and run is pretty standard. You just form their ratio. So to calculate slope, one generic description is to compare the rise to the run. You may be familiar with the phrase rise over run. So if we can measure both of these, then we can form our slope. But how can we measure how far apart these are? It's actually not that difficult if you think about these in terms of x's and y's. For example, the run is how far we travel in the x direction, so let's take both of these points and project them down to the x-axis. If we drop this point down to the x-axis, it would land at 2. And if we drop this point down to the x-axis, it would land at 9. How far apart are 2 and 9? I think it's fairly obvious the answer is 7, because 9 minus 2 is 7. So we have to travel 7 units horizontally in our journey from the first point to the second point. And we can do the same thing for the rise. To figure out how far we should rise, we should see what the 2 y-coordinates are for the points and find how far apart they are. The first point's y-coordinate is 4. So if we project the first point over here to the y-axis, it lands on 4. And the end point, if we project it to the y-axis, lands at 8. And so in our journey from the first point to the second point, we rise from 4 to 8. How far apart are those? 4 units apart, which we can get by subtracting. 8 minus 4 is 4. So for this problem, we could calculate the slope by saying that the rise is 4, the run is 7, and therefore the slope of this line is 4/7. This attempt to measure slope is consistent with the idea that if the line is steeper, it should have a greater slope. For example, if the run were 7, but we rose higher, like instead of going up to 9, 8, we went up to 9, 18, then this line would be a lot steeper. The rise would be greater, which means the fraction would be greater, which means the slope would be greater. So it's consistent with the idea that steeper lines should have greater slopes. But when you're calculating slope, it's inconvenient to always have to sketch the picture if we don't have one. And it's more convenient to ask, how can we generate the slope strictly from the ordered pairs? In other words, how can we take the specific calculation and turn it into a generic calculation, aka a formula? Well, the way formulas arise in math is you solve a particular problem, and then you try to make it as generic as possible by replacing as many specific values with generic values, also known as variables. So let's see if we can replicate this, but take all the specificity out of it. For example, for this first point, instead of calling it 2, 4, let's just call it x, y, because that's a good generic name for a point. But right away, I run into a problem. I want to call the second point something generic as well. And I'd like to call it x, y, but I can't because that's what I call the first one. I could use different letters, but I really want to hold on to the x and the y because it's the first and second coordinates of each point. In math, there's a gimmick for recycling a variable when you need to use it more than one time. And that gimmick is to subscript it with different numbers. For example, if we call this our first point, then we can call this the first x by subscripting the x with the 1. You could read this x sub 1, sub is for subscript. And we could call this second x, x sub 2. And the same thing for the y's. This is our first y, so we can call it y sub 1, or just y1, or first y. And our second y we can call y sub 2. So if we generically represent our points as x1, y1, and x2, y2, how would we generically represent the run? Well, how did we specifically calculate the run here? We took 9 minus 2. So generically, it's the second x minus the first x. Second x minus the first x. And similarly for the rise, we calculated 8 minus 4 specifically. So generically, it would be y2 minus y1. Now, of course, if we don't know the values of the x's and the y's, then we can't actually get an answer to these subtraction problems. So I can't generically represent this 7 with a single value or this 4, but I can represent how we got them by subtracting. So what does that mean for the formula? Well, the formula for slope is rise over run. To generically calculate the rise, you subtract the second y minus the first y, and to generically calculate the run, you subtract the second x minus the first x. And just like that, we have our slope formula. To calculate the slope of a line, if you know 2 points, in the numerator, you calculate the second y minus the first y, which calculates the rise. And in the denominator, you calculate the second x minus the first x, which gives you the run. Excuse me. So this is the formula that we'll be using anytime we need a slope, but we have 2 points. Subtract the y's to calculate the rise, that rhymes. Subtract the x's to calculate the run, form the ratio. The only thing you have to be consistent with is second minus first. And honestly, who you call first and second is arbitrary. I could have called this the first point, called this the second point, and did y1 minus y2 and x1 minus x2. But as long as you're consistent, meaning if you call this the first x, you better call this the first y. Or if you call this the second y, you better call this the second x. As long as you're consistent and subtract in the same order, you'll get the same slope each time. In the next video, we'll look at a few specific examples of calculating slopes and what it means about a line based on whether its slope is positive, negative, 0, or one other case.